Good afternoon, everyone. Today I will present the paper Microfluidic Device with a Horizontal Motion Valve and a Localized Delay for Automatic Control of a Multi-Step Assay. This work demonstrates a design that combines a mechanical horizontal motion valve with a localized dissolvable delay, allowing a paper-based microfluidic device, or MUPED, to automatically control multi-step biochemical assays without any external equipment. I'll be covering about this article's four aspects: abstracts, materials and methods, results and discussion, conclusions. Let's start with the background. Paper-based microfluidics analytical devices, or MUPEDs, are widely used for point-of-care testing because they are cheap, portable, and require no pumps or electricity. However, MUPEDs still have two key limitations. First, they cannot easily control multiple reagent steps automatically, and their timing precision is limited because the capillary flow in paper is not constant. Previous studies have attempted to solve this by adding hydrophobic barriers or vertical valves, but those methods often require manual operation or complex fabrication. The authors therefore designed a new system with two components: a horizontal motion mechanical valve and a localized dissolvable delay region. Together, these features enable a fully automated multi-step assay on paper. And here in the figure 1 you can see a schematic of the MUPED with the horizontal motion valve. The valve physically separates the two flow paths until a sliding motion connects them. This allows precise control over when each reagent moves through the channel. Now moving on to the methods. The MUPED was fabricated by wax printing on chromatography paper. Wax barriers define the fluidic channels. The horizontal motion mechanical valve was made by stacking two paper layers. The top layer can slide horizontally over the bottom layer. When aligned, the hydrophilic channels connect and fluid can flow through. When misaligned, the channels are blocked, acting as a valve. Next, a localized dissolvable delay region was introduced. It was created by embedding sucrose or polyolane films into specific zones of the paper. The film temporarily prevents flow until it dissolves, introducing a time delay. Finally, the system was tested using an aptamer-based STIRS assay, targeting a small molecule analyte. This demonstrated that the multi-step reagent delivery, such as simple wash and detection, could be automatically controlled. And this figure in the right shows the full MUPED layout. On the left is the horizontal valve mechanism. On the right, a magnified view of the localized dissolvable delay region. The design enables precise, pre-programmed timing between assay-six. Now, let's move on to the results and discussion. The authors first characterized the localized dissolvable delay. They measured how long it took for fluid to pass through the delay region and found that wider dissolvable films produce longer delay times, while the distance from the inlet also affected timing due to increased flow resistance in the paper. By tuning these two factors, width and position, the delay could be adjusted from roughly 20 seconds to 6 minutes. This provided a simple but reliable way to control reaction timing. The delay also showed good repeatability, with less than 10% variation even under different humidity levels. After validating the timing control, the team implemented a two-step mechanical valve design. This valve allowed two reagents to flow sequentially. The first reagent moved until it reached the dissolvable film, and the second reagent automatically followed after the barrier dissolved. The transition between the two steps was smooth and consistent, showing that the valve and the dissolvable delay can work together to automate reagent delivery. Next, the author extended their design to a four-step MUPED, capable of performing an entire multi-step biochemical assay automatically. In this configuration, 4 reagents, such as sample, buffer, aptamer, and washing solution, were released in the correct order. Each step began only after the previous one was completed, controlled by a combination of horizontal valve movement and multiple dissolvable delay zones. The entire sequence took about 12 minutes, with clear, non-overlapping color flow fronts, demonstrating precise control. The device also showed no leakage or cross-contamination, proving that the horizontal motion valve is mechanically stable even after repeated use. Finally, the team tested an aptamer-based surface enhanced Raman scattering assay using this system. The MUPET successfully carried out all assay steps automatically, and the Raman spectra displayed strong signal peaks only when the target analyte was present, confirming accurate and selective detection. Figure 5 illustrates the step-by-step sequence of fluid movement in the 4-step devices, while Figure 6 presents the corresponding SERS spectra. Together, they demonstrate that this paper-based system can perform complex, timed assays without any external equipment. To conclude, this study introduces a paper-based microfluidic system that combines a horizontal motion mechanical valve with a localized dissolvable delay to automatically control multi-step biochemical reactions. Key takeaway includes: the design enables fully autonomous operation without any external pumps or power. Second, both the valve timing and delay period can be precisely tuned by geometry and film composition. Third, the system successfully executed an aptamer-based SERS assay, proving its applicability for low-cost, portable diagnostic platforms. In summary, this research represents a simple yet powerful advancement toward self-regulated MUPETs for point-of-care testing. Thank you for listening.